Alright, now that I have gotten the wild dogs under control, let's keep going. So we were talking about Glushko's experiment and looking at the neighbor effect on pronunciation, and it really implies that there's a connection between the lexical and the phonological routes. If we think about word processing and words that are accessed directly through the lexical route, so if we could ignore the sound and spelling side for a second, those words accessed on the lexical side should be accessed at all the same rate, given those regularity of sound and spelling rules, mostly because in theory these two sides are not connected, and so they should be accessed all the same, although it should be slower than the GPC side. So if we take that for a second and then look at some other effects people see in experiments, what we find is that regular words are said much faster than frequency-matched irregular words. So remember, the frequency is a big component of a lot of these, of a lot of reading, and so it's one of the biggest things. And then there's age of acquisition, imageability, concreteness. So we talked about a bunch in the last section. So one thing people have to do is make sure that we have words that are of the same type before we compare them. And that's what we do with all those databases that we used in the last section as well. So if I compare two words that are the same frequency, regular words are much faster. But on the lexical side, that shouldn't matter, but it does. Low frequency regular words are named faster than low frequency irregular words, but it's also influenced by the number of friends. So things with similar pronunciations make you go faster, and the number of enemies, things with different pronunciations, make you go slower. So they're called friends and enemies when we're talking about sound. So that implies that not only is the GPC side using lexical information for pronunciation for those non-words, the lexical side appears to use some sound rules for processing regular and irregular words. So orthography also matters. So we have with words that have low bigram frequencies. Bigrams are two-letter combinations. So yacht is a strange word because YA and HT are extremely uncommon combinations. So those tend to be kind of slow because of their irregularity in seeing them, much less pronouncing them. And these results are really explained by the race hypothesis. So the race between both sides, and whichever one goes fastest wins. And so that explains a little bit of like how these two are kind of look like they're influencing each other. So there's this table from the book, and I don't remember what page it's on, so I cut and pasted it in here, about regularity and consistency. And so some of the words we're going to use here, words that are consistent have the same regular pronunciation the entire time. Words that are consensus is almost all of them are pronounced one way except one of them. So lint, mint, there's pint. Have is a consensus word. Save, gave, wave, dave, cave, hey, have. The heretic is the one irregular exception. So it's called also like pint. Words that are in a gang are all irregular, but have one regular exception. So look, book, took is the irregular set. The hero is the regular exception in a gang. Aren't these cute? Nah. So spook. So ooh is the regular sound of spelling for double O, but look, book are the gang that are irregular. You have gangs without a hero, so all words are irregular, like cold. And then you sort of have ones that are ambiguous. So cove is a regular pronunciation, but it has a whole lot of irregular exemplars, but it's not consistent or consensus. Love is an irregular pronunciation with many regular exemplars. And then there's words like hermits, which is where yacht falls in. So very strange bigram frequencies, so two-letter combo frequencies. So all of these things are used to describe sort of the neighborhood of sounds that you get for words, so orthographic neighbors. So that's considered a pronunciation neighborhood. So friends and enemies. So friends are words that are pronounced the same. Enemies are words that are pronounced differently. And then they have this sort of hero, gang, heretic combinations of explanations as well. Oops, wrong way. We go much faster if we have a large neighborhood of pronunciations, even if they are, we have a heretic. But good readers don't show effects when we control for neighborhoods. So people who read well kind of can ignore neighborhood effects. People who read poorly are influenced by neighborhood effects. So it helps them read better if the neighborhoods are regular and friends, and it helps them you read slower if the neighborhood has many enemies. So getting into sounds a little more, so phonological mediation is the relationship between sound and meaning. So sounds have some sort of influence on meaning. Now, we've talked about how sound and meaning are, there's no direct relationship, but this is more of an idea that it can help prime the meaning. So, let's give an example. This makes a lot more sense. So in a category decision task, remember that's the idea of, is this a fruit? So we talked about this in the last section. You can say yes to pear because pears are fruit, no to pour because that is an action, but you make a whole lot of false positives to pear, spelled like put two things together. So the sound isn't tied to the meaning, like the word pear doesn't have to sound that way, but the fact that this is a homophone sort of primes its related sounding word and makes you make a mistake. So pear here, spelled this way as in two, primes the word pear as in fruit just because they sound the same. And that's phonological mediation. So we kind of connect the two because of their sounds, and that actually that sound influences my pulling up of the meaning of the word. And in this example, I make a mistake by saying, yes, this pear is a fruit. Okay. So we'll make lots of errors also in a lexical decision task with homophones. There's confusing feedback between that GPC side and that lexical side. So we think the lexical side is where all the semantics is. So when they're racing, the semantics and the sounds get kind of confused. So there's two sides to this. The weak phonological view is that there's an indirect route between the GPC side and semantics. So there's sort of this like back door from sounds to meaning. The strong phonological view is that we get meaning from the way it sounds, and you can't recognize those words without that sound. And this is the idea of inner speech. I would say some more people are in like the medium phonological view, because you do have people that don't have inner speech, that don't show these effects, that don't have problems with dyslexia and sound, deaf people. So there's a lot of complications to this idea, but the idea is that we use that sound to give it meaning. And that is pretty true, but how strongly we do that is the question. So some support for this idea that sound leads to meaning. Now this is not sound is meaning. That is not true about language. The sounds and the meanings are ambiguous, but sound leads to meaning. So sound accesses the dictionary definition of a word. Okay? So people will stare a lot longer at the word soul like shoe and soul like soul in your body, even though the spelling makes them not ambiguous. So the sound between those two words is ambiguous. I don't know which one you're talking about, but spelling-wise it's very clear. But people will look at them a lot longer because of that inner speech. It might be only that poor readers do this because they're focusing only on sound sides instead of also orthographics, the way it looks. And that really only tends to happen for low-frequency homophones. So if it's a higher frequency word, we'll rely more on frequency and less on sound. If it's a lower frequency word, kind of all bets are off. Okay. And so here's an idea. It might be that you're racing the lexical route, and sometimes that route's kind of slow. So the GPC route has some time to put together the sound, And so they come together at the same time and you're forced to make a decision. These sound the same, they look different. I guess I'm going to focus on looks, but sounds are so compelling, and so you're basically just kind of confused. And some of the reasons, some of the support for this phonological mediation is this idea of inner speech. And so when you are thinking to yourself, you hear yourself in your head. If you are reading, you'll often hear it in your brain. And so what's happening is they think it's activating the phonological code during silent reading. And that's actually pretty much true, because what they do is they have people read things to themselves, not aloud, in those fMRI machines, and they look, or MRI machines, and they look at their fMRI, and what you see is if you're reading, it activates Broca's and Wernicke's and the strip of your brain as if you're actually talking. So reading involves actually speaking as well, and that's the idea of embodied cognition. The thinking about doing something is the same as doing it. Now, I wish I could think about running and it'd be the same as actually running. It doesn't work that way, much to my chagrin. But when you are reading, it acts as if you're reading aloud. And so some sort of interesting research in this area is that tongue twisters take people longer to read. And if it was purely based on meaning of the tongue twister, that wouldn't happen. But because it's a sound issue, it takes you longer to read because your brain is trying to sound it out. Inner speech does help with comprehension. It's a good thing for you. It helps you put information together in working memory. So inner speech is actually good. Sometimes people argue that it's bad for you because it slows you when reading, but slower reading does, to an extent, encourage comprehension. Quicker reading slows comprehension. So there's a nice balance between reading speed, inner speech, and comprehension. So what about the times that you have to know what the meaning of the word is to create the sound? So I could talk about a bow, to tie it in a bow, or I could bow, I could tear something, or I could tear up. Read and read are different morphemes for the same word, so people don't tend to use that one. But this is really where we're talking about the word's meaning changes the way it's pronounced. So I tied my shoelaces in a bow, I took a bow. How is that going to work with this dual root model? Because at the moment, semantics are all on the lexical side, and sounds, it's not sure which one to pick. Okay. And so one thing we have to do is figure this out, because we don't have a good example for this. What they think happens is that there again is this little sort of dashed line between semantics. I'm going to show you that model here in just a couple minutes. So what about speed reading? We talked about inner speech. What about speed reading and the speed reading courses and read faster and remember more and life is great? Those courses don't work. Don't waste your money on them. Because once you increase your reading speed above what's considered a normal rate, comprehension declines. So you might get through reading your biology book faster, but you're not going to remember it. So in the case of schooling, speed reading is not a good idea. One thing they tell you to try to do when speed reading is to turn off that inner speech. But the inner speech actually helps you, so I don't know that it's the best thing, So, I did some research on this. Justin Carpenter are really big researchers in the reading area. And what they did was they gave people an easy text to read and a difficult text to read, and asked people, normal people, to read them. And so normal people did much better on remembering what it was about. And then they asked speed readers to read them. And speed readers got the gist, so the basic overview, but if you asked them specific details, they were total crap at it. So we were able to show that normal reading is much better for comprehension. Speed reading is really good for getting kind of the basic overview. Because speed reading is basically skimming. So for comprehension, I really need that information to stay in the fovea just a little bit longer, to go through inner speech processes and really get integrated into the overall picture of what's happening, which is not quite what we're covering here. But for comprehension, I need those things to happen, whereas speed reading is focusing on sort of skimming as quickly as possible, which turns off some of those features. So, we've got some issues with our simple dual root model. There are lexical effects of reading non-words, so the homophone, pseudo-homophone effect on non-words, but that should all be the GPC side. Then we see the effects of lexical regularity on pronunciation, which should be the entire lexical side. So it appears there's some sort of connection between the two, and so we have to figure out what that is. And the way to do that is actually to study dyslexia. So I don't think the answers to the dual root model question of where semantics comes to play can be answered with sort of normal folks. You have to tend to look at problems with reading to understand our basic processes better. So in all of these sections from here on out, we're going to talk about problems with the thing that we're focusing on because it helps us understand what's going on better. So there are two basic types, four, I can't count. There are acquired disorders. Acquired disorders are caused by brain damage, and disorders caused by brain damage is acquired with a D if it was previously intact. Okay, so it is a disorder caused by brain damage is acquired if it affects, let's just say changes, an ability that was previously intact. So a little bit of brain damage, you no longer have working memory, that's an acquired disorder. A developmental disorder is a disorder where the normal development or acquisition is affected. So these tend to be things that you sort of see slowly come on. Dyslexia tends to be a developmental disorder. It's technically a disorder of reading, but what we think the issue is sound often. It's not always sound, but in a lot of the cases are sound-based. It is not a problem with spelling. Spelling is an output problem, so it's one of the effects of dyslexia. And there's also dysgraphia, which is a disorder in writing. We're mostly going to focus on dyslexia and acquired dyslexia. The two types, central, which involves higher level processing, and peripheral, which is lower level processing. We'll get into those a little more here. The basic one I want to focus on is surface dyslexia. Just kidding, there's three. Phonological dyslexia and deep dyslexia. So surface dyslexia is where a person has trouble with those exception and irregular words. And so they will try to pronounce them as regular words. So have would be pronounced have. So we over-regularize errors. So we pronounce those irregular words with regular sound and spelling rules. And that is a breakdown of the GPC lexical, non-lexical route. Okay? So we're trying to pronounce everything as regular because we don't have any other options. Okay, so surface, the way you have to think about it is like it's a problem with irregular words. There's two types of surface dyslexia. Type 1, where we're highly accurate at reading regular and pseudo words. We can't handle irregular and non-words. Type 2 is where we can't handle irregular and non-words, but then we also have trouble with some regular words. So it's actually just a sliding scale of how much this affects our ability to pronounce regular words. Irregular words are none. Phonological dyslexia is where we can pronounce regular words quite well, but we're poor at reading non-words. So we can't sound it out. So we think that's a breakdown in the sound side. Okay. So we can't read the non-words because there's no way to sound them out, and we read irregular words just fine through the lexical route. Okay. So this is surface dyslexia is really a problem with a lot of the lexical issues. We just say everything is regular, whereas phonological dyslexia is more of a problem with the sound side, where we say that we just can't sound things out. Oop, did I skip a slide? No. All right, so phonological dyslexia is probably the most common, so let's talk about that one. People are better if they're pseudo-homophones, so that integration between those two sides, it helps you out. You do have trouble with words that require an inflection, so emphasis is a good inflection word. Derivational errors, so we'll actually read a relative of the target, meaning it's like a very similar word grammatically, but isn't quite the same word. And a visual error is words that look the same, and so we'll get them confused. Like perform and perfume look the same, so you'll pronounce the wrong one. And this does seem to be a bit vision-based. It's not totally about seeing the word. This was previously we thought dyslexia was a vision problem, which is not true. We do tend to see some trouble with complex phonemes. So AU is a very complex phoneme for English speakers, and it has lots of different pronunciations. But for spellings that have a one-to-one mapping, like IKO, there's only one way to pronounce that, we're much better. And then some people seem to be sound-based, so they can read those pseudo-homophones because they kind of look like another word, but not non-words. So one thing in this, especially this section, that you're going to see is that the results are really messy. So it's difficult to tell because sometimes what we think happens is that people don't just have one type of dyslexia. They have kind of a range of issues, and we tend to classify them as like you have phonological dyslexia so that they can get the right type of treatment for the main bulk of the issues, whereas they might actually have a little bit of both. But it's easier to fix most of the problems by focusing on this one. And so people, you can't put them in nice little boxes here. And that makes this research really difficult and sort of messy to tell what's happening because people don't tend to be just one thing or another. So, in sum, this isn't the end, but in sum to the kind of a lot of what we've been talking about. What happens in that GPC side that appears to access lexical effects and semantics because of the pseudo-homophone effect and a couple of other little things that we've seen, phonological mediation. What is going on in that GPC box? So there's kind of what we think is 3 stages. There's a grapheme analysis where we're taking those letter streams and putting them into our little graphemes. So graphemes, not quite syllables, but close. There's print to sound conversion where we assign the sounds to those graphemes. And then there's the blending stage. So the way that they're kind of all smushed together to actually be pronounced. Okay, so we think this is all within the grapheme side of that model in that box. And it's sort of a breakdown of how we think that thing is happening. And with this, that's going to come back here in a minute of understanding how semantics gets involved because of deep dyslexia. So deep dyslexia is a problem with semantics. It's not really sounds and it's not really looks for lexical access, but it's a problem with meaning. So what you see is that it tends to look the same as phonological dyslexia, and this is really rare. So it's difficult to study because it's so uncommon. But it's sometimes called semantic paralexias, where we get a reading error based on the meaning. So this is where you're going to have trouble knowing the difference between bow and bow, and read and read. And what was the other one? Tear and tear. And one interesting thing that you'll see people do with this is instead of coming up with the word that you're trying to pronounce, so let's say you're looking at the word daughter, what they'll say is sister. So those are not, they don't look the same, they don't sound the same, but they have a similar meaning. And so what's happening is the looks and the sounds are just dunzos, and you're getting it based, you're trying to connect it based on meaning. So you'll see people make semantics errors, so words based on meaning, visual errors, so we'll get confused when things look the same, perform to perfume. We'll incorrect function words because it's sort of like all function words are the same. Remember, function words are prepositions, the and a, those sorts of things. derivational errors, so we'll do the wrong verb, and we can't pronounce non-words. So it's kind of a hot mess. There's a lot going on. And so a couple of these are also surface and phonological dyslexia problems. And then some interesting effects is this imageability effect, or imaginability effect if you want. And remember from a couple sections ago, that is when it's easier to read a word if we can form our mental image of that word. And so that effect tends to go away with deep dyslexia. Nouns are easier to pronounce than adjectives. Adjectives are easier than verbs, and function words are just the hardest thing because they're kind of all jumbled up. And you'll see this sometimes with people where they'll say, I went to see a dogs. So those things don't match. It should be the dogs. That's when you'll see problems with function words. And prepositions. The preposition won't make sense. So if you were to have deep dyslexia, writing is impaired, auditory short-term memory is impaired, so that's some of the problems you see with sounds, and the reading ability really depends on context, because semantics is what's kind of screwing things up. And the issue we have with studying this and understanding it is that, one, it's rare, but two, they vary on their symptoms. And so sometimes they have more phonological issues, sometimes they have more looks issues, sometimes it's all semantics and they don't have problems with either in singular. And so it's difficult to know what it is that's causing it, and they think that there are probably multiple ways that this happens. But it just does make it harder for us to model what's going on. So a couple types of deep dyslexia. So there's the input type. We have trouble finding the meaning of a word when reading. Central type of dyslexia is when we have auditory problems when we're reading. So when we're reading words that sound the same, you'll get confused on which meaning it should be. And then the output problem is that we can get what the semantics is, but we can't pronounce it. So we have trouble with making the sounds. So to explain this, there's a theory called the right hemisphere hypothesis. And I just am trouble with the past tense words here in this set of slides, but the more the left hemisphere that's damaged, the more severe the deep dyslexia. Remember, left hemisphere is mostly language based. And so what'll happen is the brain is plastic to an extent, and so the right hemisphere will pick up the slack, but it just doesn't know how to handle all this language stuff. It is the very, very simplistic view of this hypothesis. So when we have damage to the left side and the right side picks up the slack, it just is not doing a good job. So remember, all of these are acquired dyslexias. So these are dyslexias caused by brain damage. Okay. And so what we have to do now is revise our dual root model to really explain acquired dyslexias and some of the effects we see between surface phonological and deep dyslexia. So I have a picture of that somewhere here in a couple slides. So let me back up. What we're going to add is a non-lexical route for putting together pronunciations in the GPC. So we've got our standard sound and spelling rules, but then also a sort of separate rule-based thing that allows those orthographics, looks, and sounds to affect each other because of all the different things that we've seen in these experiments. So now there's a semantic direct route and a non-semantic direct route. So what we have is our grapheme phoneme correspondence over here, our non-lexical route, and it's got those three little steps in it. But then we also have sort of a semantic direct route over here, but then within the lexical route, which we thought was all looks before, so the new piece here is these two little things down here. We can have orthographics affecting phonemes, but we can also have meaning affecting phonemes. So we think that this side is just much more complicated than we thought. But if you think back to the last section when we were talking about understanding the lexicon and the way that words are stored, this shouldn't be a big surprise, because we really thought that words were stored with their meanings, their looks, and their sounds together. So why would we argue that sounds are totally separate? But what we think actually is the relationship between written symbols and sounds is sort of its own special thing, but they do interact together. Okay. So that's sort of the end of the dual root model. We'll come back to it here in a little bit, and we're going to do a couple of other types of models, but as you can tell, since the majority of this lecture has focused on the dual root model, it is the most popular. Okay. A second model is the analogy model. There's just a single route. It's all about pronunciation, and it's all by analogy. Okay. So pronunciation really occurs by making analogies to similar words. This is kind of a neighborhood effect. So when we get one word that's activated, it activates its neighbors. When the neighbors are all normal, this is sort of the gang hero thing from a couple slides ago, or the neighbors are all rhymes, pronunciation is fast. When a neighborhood is sort of a mix of different things, not cohesive, you slow down pronunciation and sometimes errors occur. That does not explain the frequency effects on regularity, though, very well. One problem with this model is while it's cute, it doesn't seem to explain a lot of things very well, and it just would make incorrect predictions about how people would pronounce certain types of words. It doesn't help us understand how frequency affects these things and how meaning affects these things. So it's not a very popular model, but it was one of the original models of naming. Okay. The other sort of big model in comparison to the dual root model, and I don't think these two things are necessarily at odds with each other, they just they could work together, is a connectionist model. So when we talked in the last section about foresters and the logogen models, I said, well, then we've also got PDP, parallel distributed processing, this connectionist model, super popular. It's Rummel, McCullen and Rummelhart, and it's got these 3 levels. It kind of looks like a balloon, if you can remember. Well, McClellan gets around, so he also has several models on Seidenberg, looking at how this affects naming rather than just recognition. So this is the step up, right? And so they have a sort of little cute triangle model, and these are connectionist models. So these are bubbles. These are hidden units or hidden layers of your brain that we're not totally sure what they do. And this model is fairly popular for explaining a lot of the things we've already talked about with pseudo-homophones and dyslexias. So let's talk about how this works. And it's very similar to that interactive activation model or parallel distributed processing. Reading and speech involve 3 pieces: the way it looks, the way it sounds, and what it means. And all of those are connected to each other, and they feed back into each other. So there's no separate side race system. It's that they're all connected and they're all kind of talking to each other all the time. And that's the biggest contention between the two, although they're not totally dual root in this model, they're not totally separate things. So a little bit about how these models work, because it's so interesting. So backpropagation, which just sounds horrible, is a mathematical algorithm for how these things are trained. So we back up. So we've got this model, and within each of these bigger bubbles, we've got lots of little bubbles, and so we actually teach these models as if they were baby humans, and train them in a way that we would expect people to be learning words. And then after training, we sort of give them new words or new things in the model and see what it does. Does it act like a human being or does it not? So this is kind of blending into AI just a little bit. But they teach these models, and what they use is called backprop. So backpropagation it gives it input, you get an output. The output is either told you're right or no, you're wrong, and then the information flows back. And that's very similar to the way children learn. So they get some input, they say something, and then they wait for a reaction from their parents. And so if that reaction is positive, the backpropagation says, yes, you were correct, all of those connections are strengthened. If the action is negative and you're wrong, those connections are weakened, and the right ones are strengthened. So it's sort of a stimulus response kind of back and forth in learning. Right? So we're changing our connections, much like your brain remaps when learning. Okay? The interesting part of this to me is these Wickel features. These are not super popular anymore, but Wickel features is this idea that phonemes are represented not by one particular little bubble, but by an activation of bubbles. And that's probably not too far off from how our brain works, is that this pattern of neurons is like a barcode for phoneme, but they weren't super popular when they first came out in these models of naming because they're a little odd. But the idea is that instead of each phoneme has its own little bubble, it's that phonemes activated in parallel are specific combos are sounds, kind of like binary code. So the way they did this is they trained the model like children. So they would activate those orthographic units. Here's the way it looks, have that feed into here's the way it sounds. And they did that in a way that children would learn the frequency and the age of acquisition rules, so they wouldn't give people irregular or infrequent words more often than frequent words. So we train them like you would real people. And then after the training, it appears that this model seems to work pretty well. So you get the same types of phonological problems that you would in a naming task, the same types of orthographic problems that you would in a lexical decision task, and the speeds are the same as what real people would do. So this model is looking pretty promising because it matches what people actually do. And that's always a struggle when you're going to do computer models, is making sure they actually work like people, because otherwise they're just fancy, non-real things. So, the newer version now is the revised PSMP, I don't remember what order they should go into, but it's probably the one on top, but I did the abbreviation wrong down here. But what's happening is it's the order of the names of the authors. So we've got Plout, McClellan, Seidenberg, and Patterson in some combination. There's a bunch of papers on this, and so I think this particular paper is where the names are stuck. So this does not abbreviate to a particular name for a model. It's the author's names. So I wrote them down here so that it wouldn't be confusing on what this was trying to represent. Okay, so this is a revision of their connectionist model. And so that original model did bad because of these Wickel features. So those were not popular. It didn't want to make that connection between gave and save, even though they are phonological neighbors, and their activations wouldn't match. So we're missing something here by using this barcode kind of hypothesis, because those two things should match because they are phonological neighbors. And so what they did was they trained the model differently with more of a realistic phonological restraint. And those orthographic units were constrained to letters that occur together in language. So instead of just single letters, they kind of focused more on bigrams, combinations of letters that would occur together. So you would never get QP together, that sort of thing. Okay. They added more semantic connections and made orthographics go to semantics directly. It used to have to go orthographics to phonology to semantics, I think, but they allowed it to sort of connect across all of the different ways, as opposed to forcing it to flow in one direction and then back in another direction. So instead of being a tiered model, we made it this triangle model. That seems to work better. So these models mimic what real people do. Do they explain dyslexia as well as that dual root model? Because the dual root model explains dyslexia pretty well. So how does this model do? How does it stand up to dyslexia? Okay. So with surface dyslexia, we can cut out those hidden units. So those hidden units, let me back up, a little more slides here, are these little connections between the two. So the original model did orthographics to phonology, phonology to semantics. Now it's just this big circular triangle. But surface dyslexia, we're going to cut out these blank pieces. All right, where are we at? Here. By resetting the weights to 0. So they trained the model and then they wiped out all that training. And what they found was that sometimes the model will reset themselves back So if you're sort of training, so think about this like a video game. You're playing your game, and then part of the game wipes itself out. And so sometimes it'll kind of come back on its own, and that's maybe why we get these weird effects with dyslexia that we can't totally figure out, and sometimes they don't. And so that's why dyslexics show different effects, even though they technically have the same type of dyslexia. For phonological dyslexia, it was easy. You could just knock out the phoneme representation, so it's phonological impairment hypothesis, and you just have trouble with phonemes, so just take out that phoneme part, and it tends to mimic the effects that you get from phonological dyslexia, so that one was fairly easy to explain. Deep dyslexia is the tricky one. So what they did was they trained the model to associate pronunciation with meaning, which we do naturally because that's how I understand the difference between bow and bow. And they have these memes, I guess is how you say it. Memes. Could be like Little Mermaids. Anyway, a semantic representation added to that pattern of activation. So I've got the activation for the way it looks, I've got the activation for the way it sounds, and it also is meaning. So the looks and sounds combo activates its meaning. And then they've added these new things called cleanup units. So cleanup units are clearing up the mess. So it allows there to be this complex relationship between the way it looks and the way it sounds to create a picture of what it means. Because with especially bow and bow, the way it looks doesn't disambiguate meaning, sound does. So the look plus the meaning, the look plus the sound equals meaning. And so these cleanup units kind of allow that combination of looks and sounds together to tie itself back to meaning. And so it kind of models these complex issues. If this model were to be talking about actual reading, like getting into context effects, these cleanup units would be part of that context issue. So in this last section, we talked about how if you're reading along and a word matches the context, you only activate one of its meanings. That's kind of what a cleanup unit does, is that it kicks out those other meanings. This is also considered what's an attractor network. So attractor networks are really complicated to explain. They involve a lot of 3D pictures. But think about attractor networks as this idea of a pattern of activation. So I get this pattern, and it creates this then word for what you're doing and the meaning for whatever you're trying to read. And it's a point in the network at which it sort of like says, here's the pattern, so the whole thing fires. And so related combinations are sort of attracted to each other. They create this sort of pull together. And they think that paralexias occur because we have the same pattern of activation, but you sort of get the wrong word. And so the way to think about this is, I hate to say glitch in the matrix, but that's kind of the idea, is that those patterns are so similar that you think it's one thing, but it's actually another, but the patterns are so close you can't tell the difference. And so you're just kind of pick the wrong one. This is sort of explaining that daughter-sister thing. Their activation is so similar that you just can't distinguish between the two. Okay. So all of that taken together, which one wins? So we've got the dual root model, and we've got this PSMP model, PMSP, whatever it is, the connectionist model. Like, which one's more accurate? And probably the most realistic thing is a combination model. Now, people have proposed combination models between the two, but these tend to be sort of different researchers, so they don't always get along. Let me find my picture here of the revised dual root model. Where is it? This, here. And it might be, if you look at this model, here's the dual root model, here's the connectionist model right here. And so it might be that they're, instead of direct like links, so I can only go orthographics to semantics phonological, is that this is a feedback loop. This is the connectionist model, but it also includes this other dual root race idea. And so they might both be right, and you can integrate them together. But all of that taken together is models of reading. In some of the next sections, we'll get into how we go from reading individual words to conceptualization of meaning in reading, so discourse processing.